Okay, so let's continue. And that's the transformation matrix between the displacement components. Not, it is not the same displacement vector. It is related to the kinematic condition. If we know the nodal displacement at the point A, then we can calculate the nodal displacement at the A prime. Since it is you can say they are the constraint equations, or you can say they are the kinematic condition. They are the kinematic conditions. Also, we can calculate the relationship between the force. Okay, let's say we have the force. Okay, if we know the member end force at the A prime, then what will be the equivalent force system? That's the member end force at the A prime. Okay, and then if we like to calculate what is the equivalent force okay, if we know a set of the force which is applied to the A prime, but since we have the rigid assumption, it is a rigid body. Okay, since we know from the A to the A prime, it is the rigid end zone, so we can calculate the equivalent force. The equivalent force, we can move the pxa prime directly to the px. Okay, since as long as these two forces, the magnitude of these two forces, they are the same value, so you can move the pxa prime directly to the point A, since they are along the same straight lines. And what will be the MA prime? The MA prime will be moved here, and the PYA here, the MA is equal to MA prime plus PYA prime times A prime from AA prime. Okay, from AA prime. Okay, so we can write the equations for the force transformation. Okay, so if we know if we know the pxa prime, PYA prime, MA prime, then what will be the equivalent force system? But the low point should be changed to the A. From these equations, this one is 1, 0, 0. And the PYA is also equal to PYA prime. And for this one, this is the 0, AA prime. Okay, so that's the force that's the this matrix, which is just the transpose of the displacement relationship. Okay, that's the transformation of the displacement. The transpose. Okay. Then we can check the second rigid end zones. The second rigid end zone from the B prime to the B. Okay, and again we assume we know the which is like this one. So we have if we put them in the matrix form. Okay, so that's the force transformation. And what is the if we have the end force which is applied to the B prime, and we know from the B prime to the B, they are the rigid end zone. So we can calculate the equivalent force system. If we change the force system here to the force system applied to the B, what will be the equivalent force system? And for this one, should be the 1, 0, 0. If we know the Px B prime, Py B prime, and B prime, and the Py B prime will be the 0, 1, 0. Okay, and again, the force transformation is the transpose of this one. Okay, then what will be the next? Okay, so let's go back to the previous, the element stiffness matrix. We can calculate the K prime. Remember, when we calculate the K prime, we use the I, A, and the L prime. Okay, we need to use the length from the point A prime to point B prime, not the entire length of the element. And here is the nodal displacement at the A prime and the B prime. we can get the member end force on this one. And right now, the okay, remember I just put the two obtained submatrix into this one. And let's say this matrix is called the R matrix. This is the R matrix. Okay, so that's the K prime can be changed to K prime R times UA VA theta A UB VB theta B, and you can get P X A prime, P Y A prime, and A prime, P X B prime, P Y B prime, and B prime. Okay, since this vector is equal to this one, capital R times this. So K prime times R can give you the member end force at the A prime and the B prime. Okay. And if we try to change the force system to the PXA, PYA, MA, PXB, PYB, and B. It will be equal to the R transpose times PXA prime, PYA prime, and A prime, PXB prime, PYB prime, and B prime. So it will be the R transpose K prime R. Okay, and we will say for this part, this matrix